This is part 2 of building one of these big enough that I can ride on. Ah! I've already done it. I previously built a small version of the AT-AT, which was about a couple of years ago, and this was made with small 3D prints and some radio control style servos to actuate the legs. As you can see, it uses parallelograms for each leg and this interesting gear arrangement. It can also turn on the spot. No one really knows how AT-ATs turn, of course, because we've never really seen it in the movies, and it did this by swinging its legs out. That one is much smaller, of course, than the one I'm going to ride on. Look at that! Look how big it is! Look at it! The large version is made of 40/40 extrusion, metal brackets and a lot of big 3D prints, and it's got the same gear arrangement in the leg. You should check out part 1 for more on the geometry and to see how that perfectly tracks. Thanks to my 3D printing sponsors, I'm using the Lolzbot long bed printer, which is a very big bed, and I'm also using 1.2mm nozzles to make all of these gears. And all these parts are printed in Pro PLA Plus from 3D Fuel, which is incredibly tough. There's a lot more information in part 1, but each half of the leg is just powered by 2 brushed motors with gear heads, and that left me with legs that could deadlift me with no problems. I made all 4 legs in part 1, and you can check that out, and here they are. But of course we've got no body or any chassis or anything to attach them to. The little AT-AT of course had radio control servos, which means we can send them to specific positions by sending a PWM signal to them. All I've got in the big AT-AT is just DC motors though. No, I can't stop that. Let's just try it the other way. And they've got no sense of position whatsoever. We just put power on them and they turn. No. Oh, I've got to kill it before it hits the end stop. So I've designed these feedback units which go in each half of the leg, and that allows us to get a potentiometer in there so we can get the position and turn them into servos. There are lots more 3D printed parts for this part of the project, so thanks again to my 3D printing sponsor, which is Lolzbot 3D printers. This is the lid for the controller we're going to use later. We've got lots of gears and pulleys for these feedback units, and some more parts printed with a 1.2mm nozzle, which need to be really tough. I've also used the long bed again. This is actually the seat mount that's going to go right on top, so I can sit on top and ride it. Thanks to 3D Fuel for the filament for this project. You can now get 10% off at 3dfuel.com with my special code and link, and I'll get a small commission. Each feedback unit has some other parts in, including a belt, a coupler, some rods and some bearings, and a 10-turn pot. So we've got a steel rod through some bearings in a block, and that's got a nice thing on the end that stops it slipping out, and then there's a nylon washer and a gear with a pulley attached on there. That screws onto a plate which holds all the other components, and those components include a 10-turn pot, which literally turns around 10 times from end to end, and this one is 10 kiloohms in resistance. That pot is attached to the plate and it has a coupler on there, and then we've got a belt which comes off that pulley attached to the gear. And we've got a much smaller gear which is going to go onto the 10-turn pot, and that means we gear up 1 to 2. And that means for every 5 times round the big gear goes, the 10-turn pot goes round 10 times, and that gives us the maximum resolution. There are 4 legs and each one has 2 halves, so we've got 8 feedback units that have to be fitted. They go in, of course, in the top and the bottom of the legs, so we can measure both of those parallelograms and get feedback to turn them both into servos. I've attached a multimeter to one of those pots with some leads and crocodile clips, and if we actuate the leg we can see what happens. If I run the leg all the way to one end, then we get nearly 0 kiloohms, and if I run it all the way to its other end stop we get nearly 10 kiloohms, and that's the full range to the pot with that little gear going around 5 times. And that gives us roughly 28 degrees in each direction. We're going to use those feedback pots to turn each half of the leg into a servo so we can control them, but before we do that we need to put some electronics in to control it, and we also need a controller. I'm powering the controller from these camera batteries, which are NP style batteries. These ones actually have a charger and battery management built in, so you get USB power out and you can charge them through USB as well. So I've plugged this into an actual base and that gives me the actual battery voltage out, which is a 2-cell lithium battery, so we've got nearly 8 volts to power everything. I've got an encoder on my controller and an LED strip so I can see where it is, and so we can go positive or negative with that. It's actually very difficult to get to exactly 0 though, so I've actually got a switch that I can press and that will take everything to 0 when I press it. There's also some other buttons on there. Inside, we've got a Teensy 4.1, which is probably overpowered, but it does have lots of serial ports to communicate with the legs. There's a 5V regulator and a breakout so that I can take the data out, and I'm just using network cables. Basically, that's an RJ45 breakout. There's 4 pieces of electronics which are to go in each leg, and those have Teensy 4s on them, and of course the RJ45 breakout to get power from the controller. There are 8 motor drivers, and those are BTS 7960s, and each one is more than capable of controlling the 2 motors in each half of the leg. So 8 motor drivers and 4 bits of electronics. Those are mounted right here. We've got the motor drivers on the other side, and of course those 2 pots are controlled by 1 piece of electronics. So now I've turned the 2 halves of the legs using a PID controller into a servo, and that means that I can move each half by turning that encoder, and everything is proportional, so wherever I turn the encoder the leg will move to. I can use the 0 switch to set everything to 0. So at the moment I can control the knee joint and I can control the shoulder joint, and that's all very well and good, and our foot always stays parallel whatever we do because it's parallelograms. But what we really want to be able to do is define the foot position and work back what the knee and shoulder joint should be, and that means we can move all of the feet back in a straight line when they're on the ground by plotting that motion, and then we can have one foot taking steps. And we're going to define that in Cartesian coordinates, basically up and down and forward and backwards rather than the separate joints. So what we need to do is something called inverse kinematics, and that calculation is going to run on the electronics in each leg. This isn't actually that difficult. All we want to be able to do is define the length of the leg to start with, and then work out what these joint angles should be. But being as we know the other lengths of the leg because they're fixed and we can measure them, then it's very easy with some high school trigonometry to work out the angles when we know all 3 sides. And once we can define that leg length, then we want to be able to make it move forwards and backwards, but that becomes just a right angle triangle like this, or the other way, and that's also very easy to solve. And once we worked out the new hypotenuse of the triangle based on the other 2 sides that we want, both the height and the distance backwards and forwards, we can feed that length into the previous piece of maths that worked out what to do with the leg joints. I'm not going to go into the code here, but the whole project is open source, so you can find the code on GitHub if you want to have a look at it. But essentially now I can move that leg up and down in a direct straight line, and I can also move the top forwards and backwards so it slides in a straight line, at least until the joints hit their end stops. And I can do that any position, so I can make the leg shorter and I can make it longer and still slide it backwards and forwards, and that means that we can have it take steps either with the feet on the ground or off the ground. So I've decided the best thing to do here is have all of the knees pointing away from each other, and that's going to make it much better balanced because there's so much mass in the legs. If they all face forwards, which is a bit more like AT-ATs in the movie, then it means as it picks up one leg to take a step, all of that mass is pushing it forward, so it's more likely to fall over forwards. So I did think about reversing them all so they all point the other way, which is a bit more like Spot Mini, but then obviously I've got the same problem when I walk the other way. And I could have faced them all inward as well, which is a bit more like an actual dog or something, but I think I'm actually going to go for them all pointed outwards because then it's better balanced and it looks more stable. Our inverse kinematics is working well, but actually what we need to do now is plot the motion for each foot, which is going to move all the way back, and it's going to take a step, and we're going to cascade all the feet. And to get these to move in perfectly straight lines, what we need to do is in fact plot all the positions from point A to point B, probably 100 times a second, so we get a nice smooth path. And we're going to feed that back into the inverse kinematics. I'm not going to go into the code too much here. It's pretty much the same as all the other walking robot projects I've made, including OpenDog 3, which you should check out. I'm using the Arduino ramp library, which will interpolate between 2 points over time in a smooth line, so that will plot all the positions for you between point A and point B, and we can feed that through the inverse kinematics. Now, OpenDog 3 was moving his legs a lot quicker, so it's harder to see the path of the foot, but we're definitely going to see it with this AT-AT because it's huge, and it's going to move really slowly, just like AT-ATs in the movie. My controller is now sending those walking motions to each leg so they're all cascaded, so you should be able to see all the legs moving smoothly from right to left along the top. If I just grab the camera and we'll have a closer up look, and then seeing one leg cascading, moving down slightly and back a lot quicker, so it's taking steps. And that means all those feet should move smoothly along the ground, meaning that the top of it goes in a perfectly level path, and then each foot cascades to take a step. So this is looking pretty good. It looks like the legs are all doing what they should do to walk along, but we're not going to really know if it does walk, so we put the chassis on top and link all the tops together instead of all the bottoms being together on the ground. A massive thanks to Simply Bearings for all of the bearings in this project, including these Lazy Susans that allow the legs to swing out, and all the other bearings, of which there are hundreds in the legs because of all those parallelograms, and there's also some collar clamps on the end of all of those and in the other mechanisms as well. I actually outsourced all this cut aluminium to Xometry, even though they're not sponsoring the video, because it was almost more economical than doing it myself, and some of these plates also came from a DIY store because they happen to be the right length. I've got these 4 units which go on top of the legs, and that makes kind of a parallel thing, so we've got something to brace it, because those are going to be hung on the end of the chassis, and we don't want them to be all floppy. Each Lazy Susan is bolted onto 2 pieces of 6mm aluminium plate, and those you'll notice also have holes so that we can attach them to some 40/40 extrusion, and this is going to make up the basis of the leg swing for the chassis. That's then double-deckered up with another 2 plates and another Lazy Susan and some more 40/40, and these plates across them to hold them together, and that means the outside stays still and the middle will rotate. We've still got more to add to that though, with another Lazy Susan, another 2 6mm aluminium plates, and some more 40/40s and some more plates on the side, so we get this double-decker thing with 3 Lazy Susans, and there are these angle plates on the ends which we're going to attach to the legs. This is looking pretty substantial. I need to lift this up and put it in between the 4 legs, all these brackets attached to the legs, but I'm pretty sure I can't lift this up and get it all aligned by myself. It's going to be really difficult because there's quite a lot of mass in it. So it's time for a quick ad from the video's sponsor, which is FlexiSpot, who make office chairs and standing desks. And we're actually going to use the standing desk to lift this up like an engine hoist so I can get all of this aligned and get it bolted to the legs. I've got the FlexiSpot E7 Pro standing desk here, which is actually quite heavy. The box was extremely heavy when it came, and it's extremely substantial. It appears to be made of steel. So here are all the pieces laid out. It's very well packaged, and it also comes with an extremely comprehensive set of instructions, which are actually written in very good English, which is good to know. So it's very easy to put together. It's extremely substantial and can lift a person with no problems at all, and it probably goes much lower and much higher than you'd ever need for a standing desk, but it's really useful for me because I can get extremely high. It actually goes much higher than I was expecting, so all I need is this wooden box and then I can put my chassis on and I can lift it into place really easily, which is going to make putting the legs on much easier than if I try and do it manually. So that gives us just the right height we need, and the standing desk will actually go higher. Now I can bolt on the legs with those plates I've got, lots more T-nuts and some M5 bolts. Once I've got 2 legs on, it's easy to put the other 2 on, and I can just drop the box and the standing desk out of the way. Using the desk as an actual desk has been very useful as well to get my laptop and the controller and my cup of tea at the right height for working on the code for the AT-AT. And also, if I want to work right up the top, then I can lift myself up with everything, including my laptop, so I can poke around in the top, check where my wires are, and look at the code at the same time. It really does go very high. FlexiSpot also sent me the C7 chair, which is a proper ergonomic chair for working and sitting at a desk. It does have this footrest and it will go right back, which is very comfortable. I could almost fall asleep in there. All the parts are adjustable, including the lower backrest, which does of course lock in place once you've got it in the right position, as do the other parts, including the headrest, which adjusts in 2 axes, and of course the armrests, which go up and down and they rotate, and they also go backwards and forwards. FlexiSpot provides all kinds of standing desks and ergonomic chairs to meet your demands. If you want a really stable frame for premium use, I'd recommend their E7 Plus standing desk with its 4-leg design. And they also have comfortable ergonomic chairs with flexible adjustment for your back. Use the promo code Bruton30 for $30 off both the E7 Pro desk and the C7 chair. So I've got all 4 legs bolted on now and everything is together. There's also a linear actuator at the back that's going to control that leg swing, but you'll have to check that out later in the video. So this is all the mechanics together. I guess my concern is now if the chassis is going to be rigid enough or it's going to twist. So if we pick up one leg, are they going to kind of like flop together as the chassis twists? Because we've got quite a lot of mass hanging out here. So I guess I better power it up and pick up one leg and see what happens. Ooh, okay. So yeah, there is a bit of flex in it, but it's nowhere near touching that other leg there, so I think that's going to be all right. But can it walk? So it does this little sequence to put the legs in the right position, and then it starts walking. So it looks like it can walk, which is pretty good. But can it walk with me on top? Well, there's not much space up here at the moment because the ceiling's not high enough. Oh my god. Oh, that'll have to do. Oh, right. Okay. Let's go. Oh my god. Well, it's not tipping over too much even with me on top of it. It is a little bit. Right, all the feet are in the right place, they're walking, so step 1, step 2 on this side, step 3 on the back. I can feel it tipping a little bit. But it seems to be rocking when it's putting its feet back on the ground again. But that's actually carrying me. I can't believe it, all those 3D printed gears. Well, there you go, that's a testament to how strong 3D Fuel Pro PLA Plus is. Those tiny gears on the motor, they seem to be holding up. Well, this is bonkers. Right, I don't want to run into the wall, so I'm going to stop the walking sequence now. Right, now he puts all his feet straight. Right, I can't get down now. That's my radio mic. This is the power distribution that I've wired in, which is 6 LiPo batteries, 3 on each side, and then I've got some bolts to make a power distribution thing, and I've also got a 200 amp contactor there, so that actually will cut all of the power, and that's linked to an e-stop switch, so we can cut all the power or turn it on and off. I've made this sliding piece on V-wheels with some rollers for a big stick, and that goes between where the seat is and where the head is going to be mounted for the AT-AT. You may remember my friend Billy from the recent World of Warcraft promo I did, so Billy popped back in to make some cosmetic panels for the AT-AT, and that's because otherwise it looks a bit like a bag of sticks. In the last video, some people said it even looked like Lego. Here's a little preview of the head, which you can check out later in the video. Most of these parts are made from foam boards, some 10mm and 5mm EVA foam, conduit, some 3D prints and all sorts of things. All of this needs a grey base coat, so we're out in the garden again because we need to use the spray gun, but obviously it's Britain, so the weather was really rainy and windy. So Billy did a base coat on all of these with a nice grey, which is basically acrylic paint for the spray gun, and then did some detailing with some brushwork and some skills. And it's all getting weathered, at least with the limited time we have, so it looks like it's a working AT-AT in the Imperial Army. this car's rubbish. It's got switches in here, I think, and all it does is full speed and full speed reverse, and then all it does is like full lock and nothing else. I've got a better idea. It really is an exhilarating experience being up here. I can't see anything in this helmet, but it is carrying me. It feels amazing. All the functions are working, so I can walk along and I can turn on the spot, and that actuator's pushing those legs out. It's picking up 2 and it's pushing them out, and then putting down 2 and picking up the other 2 and bringing it back together again. That's causing the legs to spread, and I can just feel myself turning round and around and around. Feels amazing, and I can't believe all these plastic gears have held up. The head stick's working well as well, so that's pointing forward, and that's on my rotating seat, Lazy Susan. That bungee's holding everything in the middle. Obviously it's not very fast. We worked out it does 60 meters per hour, which is 1 meter per second, which is 0.037 miles per hour. I reckon if we walk with 2 legs instead of 1, we can make it quicker, and if I overdrove the motors, I could probably get it to go twice as quick. But I'm just pretty impressed it's come out this tall and it doesn't fall over, and I'm on top of it and I'm doing all right. If you'd like to see another video on this, then let me know in the comments. I'm probably going to do an improvement video where I make it go quicker, maybe put a body on and maybe some weapon systems. Thanks again to FlexiSpot for supporting this video, and that's the chair that I'm sitting on, of course, and the standing desk that I used to get up here. If you want to check out my Patreon, then you can do that as well, and patrons get access to all the videos early.